All right, I'm here to introduce the person who's going to introduce the person who's going to speak next. So when I first arrived at UMass, our number of faculty in computer science was in the 30s, maybe the low 30s. We're now in the 60s, and maybe on our way towards 80 or higher. And we've become a college of computer science, not just a department. And we're thrilled to have as our first dean, Laura Haas, who had a very distinguished career as a research leader at IBM Almaden, recently received the Computer Pioneer Award from IEEE, and has done work very relevant to this community. I mean, that work recognized work in information integration and in distributed knowledge management. So, Laura Haas.
No. Thank you very much, Andrew, but I'm really here to introduce our next speaker, who is Professor Alexandra Meliou. I've known Alexandra since her graduate school days. She got her PhD from UC Berkeley, went and did a postdoc at the University of Washington before joining us here at UMass. I am particularly fond of Alexandra's work because, to me, it really epitomizes, in my own space, in the space of data and data management, the research. I've got myself in a mess. The research that we want to do directed to what we call computing for the common good, which is kind of an overarching theme for the college. Alexandra has noted that in today's world, we've all noted that the world is increasingly reliant on data. But if there are errors in data, if there is missing data, if data is biased, it can truly screw up what we all want to do. And so a lot of what Alexandra does is very much focused on addressing these issues of data quality generally. And today she's going to tell us about two of her experiments in that direction. So without more ado, Alexandra.
Well, thank you for the very generous introduction, and thank you for having me here. As Laura alluded to already, I'm very interested in issues of data quality, generally problems that happen with data. And I'm here to talk to you today about two particular applications that we've looked at with respect to knowledge bases, with respect to diagnosing errors and filling gaps in knowledge, and how can we do that by reasoning about the products of extractions. So to set the stage, not that I really need to do here, but when I'm talking about knowledge bases, I'm thinking about subject, predicate, object triples. So for example, things like UMass is located in Amherst. It was founded in 1863, and its mascot is Sam the Minuteman. So this kind of structured information is very helpful in several applications. We have a lot of different knowledge bases today that are powering things like search. So when you search for something on Google, you get a nice little box with structured data for the entity that you're searching for. And this structured data has been already retrieved, has been constructed by pulling unstructured information from the web. Now, the problem that we're looking at here, and it has been alluded to, it has been discussed already in previous talks, is that the knowledge that we have is not always complete. So the knowledge bases that we deal with and the applications that are using them, they deal with gaps in the data. So how is data incomplete? How is our knowledge incomplete? Well, if you search for some entities, here maybe the fonts are very small. I'm looking for a particular database conference, ICD, that happened recently in 2019, and there's no nice info box with structured information about it. And this is because this entity is just completely absent from the knowledge base. In some cases, you may get, through search, an info box that has very little structured information. So as compared to other entities that have a lot of data about them. So in these cases, the entity may be there, but the facts about it may be limited. So in both those cases, we're missing a lot of things. entities and facts are absent. So why is this happening? Why are we facing this problem? Well, there is a disparity in how popular things are. So certain information on the internet about politicians or musicians or, I don't know, movies and so on and so forth is more popular. There's more sources about them. There's more people interested in them. So those facts, these head facts, are easier to find and easier to validate. And that's why they're easier to make it into a knowledge base. But these other long-tail facts, the ones that are referred to less popular entities, things like specialized conferences or, I don't know, particular Pokemons or video games, they may not appear in knowledge bases at all or may appear in very limited ways because the information about them is more sparse compared to the head facts, and those facts are harder to validate. So we have typically these head facts in existing knowledge bases, and we're lacking these long-tail facts. But this knowledge is not absent. It's there for us to grab. It is on the internet. It's there. So there is, though, this gap between what we have in knowledge bases and what exists out there. So how do we deal with this gap? In order to figure that out, understand it better, let's take a slightly closer look at how knowledge bases are constructed. So the industrial standard is that we have a set, typically a relatively small set of sources selected by domain experts. Then through various processes, possibly including crowdsourcing and other things, we get a selection of labeled facts, and through those labels we learn patterns and we extract data, and we end up with a bunch of triples that are put in our knowledge base. These triples are typically of high quality, but the major bottleneck of this standard is that this selection of sources is typically done by domain experts, and for that reason, we end up getting a low volume of facts. Now, people have tried to resolve this by automating the extraction process. So we have automated knowledge extraction that expands the set of sources that we're looking at, and now possibly we're looking at the entire web. We're using existing knowledge bases for labeled facts in order to train systems and extract triples. Now, the problem that we get here is that it's sort of the reverse from the previous standard. We get a high volume of information, but it's of lower quality. And this is because the labeling process is less robust, there's a lot of gaps in the labels, and so on and so forth. So we end up with these two sort of both imperfect processes that end up leaving us with this gap. So what I'm going to talk to you about today is looking at the automated extraction process, the automated knowledge construction, and look at it from two perspectives. On one hand, how can we diagnose these low-quality issues in extraction pipelines? Can we reason about the extraction results to figure out why things are of low quality? And also, in the second phase of my talk, I will talk to you about how to use the automatically extracted triples in order to better inform the first pipeline. And instead of using the manually selected sources by experts in this first pipeline, to actually feed that with recommendations for sources and topics for what to extract. Okay. So we start with the first part, how to diagnose errors in extraction pipelines. So let's zoom in a little bit more to take an even closer look at what's happening. So I'm not going to get into the details that we've seen in previous talks of how all of this works, but at a high level, the way to see this is that we have a ton of web sources in various formats, and we have a complex extraction system that is sitting on top. It's getting fed data, unstructured data from the web, and it's extracting some probabilistic facts, some knowledge triples, together with a confidence value. Okay, so These processes have been employed in the wild, and there's large-scale automated extraction pipelines. Google has tried this with Knowledge Vault, and in that particular example, they have billions, more than 3 billion extracted triples. Now, the catch here, the problem is that more than 70% of them are wrong. Wrong in the sense they're labeled with low confidence by this extraction pipeline. So effectively, they're just bad, and they're going to get tossed. They're not going to get used. And this is the problem that we want to narrow into, figure out why this is happening. So traditionally, we would look at, from a traditional data cleaning perspective, we would look at where are those errors, what are the problems, and just purge the data that I have from errors, and I'm just left with, let's say, quote, quote, perfect knowledge base. But this is clearly not sufficient because I'm wasting a lot of work. I'm tossing a lot of things that I could be learning from, I could be using. The key insight here is that the data is not bad for just random reasons. A lot of the errors are systemic. They're happening because they're ingrained in the extraction process. They could be because of, for instance, faulty information on the web, bad sources. Maybe some extraction rules are bad. I learned something incorrectly. Maybe rules are correct, but they don't match the source. For example, if I'm trying to use a US-style date pattern on European websites and I'm inverting the day and the month. So if I don't fix these errors at their source, where they're actually located, this sort of pipeline will just keep producing bad data. So I'm not being very effective with just tossing the bad data that I produce and keep doing the same thing. So we really want to diagnose what the problems actually are. Now, the challenges here is that this scale is massive. We're dealing with billions of triples. The system is very complex, and the error rates are high. Because as I mentioned in Knowledge Vault, as an example, more than 70% of the triples are wrong. So we're overwhelmed by bad information. So we built a system called Data X-ray. I'm going to give you a highlight of what it actually produces and then dive into a few of the details. So Data X-ray tries to produce diagnosis that looks something like this. I don't know if you can read it, but I can explain this to you. So it produces sets of, let's call them features for now, that describe groups of errors. For example, a certain group of errors is identified in Knowledge Vault, 630 triples. Were all coming from a particular URL, bsoccer.com. They were all of type date of birth, and they all had the particular object value of 1986, something, something, a particular date. So this group, this characterization sort of describes what the problem is. What happened here is that the date of birth of athletes that was showing up on those websites were set to a default value due to copy-pasted HTML segments that someone didn't bother to update those particular fields because not all information in the HTML is actually always displayed. So, this set of features is a descriptor of what the problem is. Is this merely feature selection? It's not. Even though it does look like it. The objective here is different. I'm not trying to predict whether something is erroneous. I'm trying to explain it. The insight of why this is different is if I'm trying to optimize for prediction accuracy, I will allow overlapping features. But when I'm looking for explanations, usually an error is due to one or few things, but not multiple. So this overlap is not what I'm desiring in explanation. So the objectives differ a little bit here. Okay, so narrowing it down a little more to see what's going on under the hood. So we have a bunch of knowledge triples that are labeled as correct or incorrect. This usually comes from a confidence threshold of the extraction output. So these triples by themselves are not a diagnosis. First of all, there's just too many of them, and they're due to a variety of errors, so we need to do something better. we have some extra information about the triples. So some breadcrumbs of provenance, like which extractor worked on a particular extraction, which URL or domain was involved, what is the object type, like what is the predicate, particular values, object values, and so on and so forth. All of these can form a set of features. So now we want to group the data in such a way that gives us coherent diagnosis. The inputs that I have in this problem is each element and the set of features that I care about. And the output is a diagnosis that groups features together, produces different sets of features at different diagnoses, and I'm trying to find which diagnosis is the best. Now, this notion of best is defined by the objective function that I alluded to earlier and how this is different from just doing prediction. I don't have the time to go into the details here, but roughly if you wanted to look at the paper, there's two main contributions to data X-ray. One is the diagnosis, the cost model for our diagnosis. That tries to optimize several things. It produces small diagnoses, it picks features with high error rates, and it avoids covering correct triples, but does not exclude them. The other contribution is how we compute these optimal diagnoses, and this is done with a top-down hierarchical traversal of the feature hierarchy. So features are naturally form a hierarchy. For example, a date is part of a particular month, is part of a particular season, and so on and so forth. And this natural hierarchy allows us to explore the features in this manner in an efficient and completely distributed way. Again, I don't have the time to go through the details here, but this is the high-level takeaways. Okay, and because I mentioned feature selection in particular, I wanted to show you a brief comparison of the diagnosis that data X-ray produces compared to feature selection on the Reverb data set. And we see with respect to, so we see a recall precision and F measure. We see that feature selection does not do well because it's trying to optimize prediction. The objective function is something very different than what we need for what essentially is explanations of errors here. Okay, so what I discussed in this first part is looking at automated extraction, reasoning about the produced extractions to understand where the errors are and how we can fix them. Now, this process does not fix the problem, does not completely fix data quality in automated extraction, but it is a step towards that. Even after we have this diagnosis, it's a manual process to go and implement the particular repairs, and there's an associated cost to that. Also, this doesn't address the recall problem that these extraction pipelines have. So the problem is definitely not solved, but it's a step towards addressing some of that. So now I would like to shift a little bit from trying to fix the quality issues in automated extraction and looking instead into how we can use the products of automated extraction to inform and enhance the first pipeline style and remove the bottleneck that requires manual source selection from domain experts. So the system we developed called MIDAS, which we presented in this year's ICD a few months ago, takes the information of automated extraction, knowledge extraction, the triples, correct triples, high confidence triples that it produced, and the sources that it produced the triples from, and uses this information to automatically recognize sources and topics to recommend to the first pipeline to fix this initial bottleneck. I will guide you through how the system works through an example. So these are some facts extracted from a web source, space.skyrocket.de. They have to do with various NASA programs. So there's entities like Project Mercury, which is a space program sponsored by NASA. Now I will, instead of the triple format, I will represent now the same information a little differently in a tabular format, and I will do this because the descriptors that I will produce in the end are better represented here. Okay, so this is the same information in tabular format. I have the entities, so Project Mercury, Project Gemini, and Atlas. And now all the predicates form different attributes in this table. And I have, and the object values just fill in the cells, the corresponding cells. So every non-empty cell in this matrix, in this tabular format, represents one of the triples that we see above. Now, in this representation, these are the extraction outputs, high-quality extraction triples that I get from automated extraction processes. Some of these may already be part of existing knowledge bases that I'm trying to enhance, figure out how to fill the gaps for. Okay, and I highlight those here in my example. Okay, so now I will be working with a tabular format that we see below. Now, the key insight is that the extracted triples give us information about the sources and the topics that those sources contain, can represent, can help us with. Now, I will also define a slice of content. So a slice of content represents, now the highlights don't show very well in this projection, but basically if I select in this table all the records where the sponsor is NASA, which means all the records in this table, that represents a slice of content. And semantically, that slice of content is entity sponsored by NASA. The slice of content can be more specific. I can have two of these selection predicates. Sponsor equals NASA, and category is equal to space program. And then only the top two records correspond to this slice of content. And finally, if I do sponsor equal NASA and category equals rocket family, then it is just the last one, okay? So if I look at these three different slices that I just described to you, they have different correspondence with the triples that they match to and whether those triples exist already in the knowledge base that I'm looking at or not. For example, the first slice, sponsor equals NASA, corresponds to 7 triples in total. This is the total non-empty cells that we see in this part. But only 2 of them are not already in the knowledge base that I'm looking at. In the second slice, we're looking at 5 triples. Remember, the second slice is just the first 2 records, but none of them are new. And finally, the last slice, which is just the last row, it's looking at 2 triples, and 2 of them are new. So what I'm looking at figuring out here is how to decide which slice, which represents a thematic, a semantic content, and what source can get me the information that I need. So the slice gives me the what, and the URL, where these extractions come from, gives me the where. Okay, so the problem, as input, I have extracted triples, automatically extracted triples from automated extraction processes, and an existing knowledge base that may have some overlap with some of those extracted triples. Now, it is possible that I'm starting from scratch and I don't have anything in my knowledge base, and that's okay, everything still holds. Now, as output, I want to produce web source slices that give me some benefit in filling the gaps in my knowledge base. So the web source slices are a combination of a condition, for example, sponsor equals NASA, and category is rocket family, and a URL, which represents the source. And the problem is how to find good slices in web sources so that we can recommend them. Okay, so the objective function, so we used something in our implementation in our experiments, but it's really customizable. What you need here is to set up a function of profit that counters the gain with the gain of adding new triples to your knowledge base versus the cost of actually extracting them. Now, the challenge is that the number of possible slices grows exponentially as your triples grow. The way we address that is with a 2-phase algorithm that generates the slices in the following way. In the first phase, it initializes a hierarchy of slices by starting with the most specific slices. The most specific slices are particular entities that are fully described by all the possible selection conditions. Now, it proceeds to search for candidate slices in a bottom-up fashion, essentially by removing conditions one at a time. And this way it constructs sort of parents in this hierarchy by removing conditions. Now, during this process, it also calculates statistics and decides to prune slices if it figures out that the cost of extracting that particular slice outweighs the benefit. So it constructs and prunes this slice hierarchy as it goes. Now, in the second phase, to select the slices, it moves from top down to figure out which slice is the best one to pick based on the profit function, and whenever something has a good positive profit, it can stop there and not go below because the parent contains all the children. Okay, so this algorithm is not, in the worst case, it's not polynomial, but we found that in practice, it is very fast, and it is very effective, and it is also highly parallelizable. And ultimately, this problem is also APX complete, which means that we can't find a polynomial algorithm with a constant factor approximation for this. Okay, so some real-world examples. We applied MIDAS on Google's Knowledge Vault to see what kind of information, what kind of recommendations we would get. And some examples are, for example, this is a web page, a particular web page from the CDC, where the slice that the system recommends is to look for chemical compounds. It can look, it also finds, aside from particular pages, it aggregates slices across domains. And here in marinespecies.org, it recommends the slice to find, to look for biology and organism classification marine species. Now, our evaluation focused, and what I'm going to show you here is we focused on a small labeled set of the reverb data. You can get the link in the paper. I can talk to you about it later. So what we did is we took from reverb 100 sources. We selected 100 sources, and we manually went and judged out of the outputs, the recommendations of all the different algorithms that we tried, all the possible slices, and had human experts label them as this is a useful slice or not a useful slice. And we used this as our ground truth to evaluate our algorithms. Now, MIDAS here is in the green bars. I don't know if it shows well in the projector. And we also compared it with selecting the slices with different methods, but still using our objective function. Here is a comparison with agglomerative clustering. And we see that the F measure is much, much lower. A greedy algorithm for selecting the slices, just the top rank slice per source rather than aggregating slices or consolidating slices in domains, still does worse than this. I also want to point out that naturally the F measure of the system declines as the coverage of the underlying knowledge base increases, because it does become harder to find good slices the more information you already have, but also because of the way that we set up the gold standard, the ground truth, we're actually handicapping our system. Again, I can discuss this in more detail later, but for lack of time, I'm going to move on to runtime experiments. So with respect to runtime, MIDAS is a little slower than the greedy approach, but it's much better than agglomerative clustering, but still does quite well. So in summary, MIDAS uses the automated extraction to learn how to figure out which sources and which topics of sources would be good for augmenting an existing knowledge base to fill gaps. It is able to give good recommendations in real-world large-scale extraction systems, like we tested it on Google's Knowledge Vault. So just to summarize what I talked to you about in this talk, we looked at the gap in knowledge bases compared to the information that's out in the web, and how this is reflected in the way that we generate knowledge today. The promise of automated extraction processes, I think, is great, but there's a lot of problems to solve. In the meantime, while we're solving them with things like figuring out how to correct errors like I presented here, I think we can use the information that we gain from them to improve the other processes that I use, as I presented with Midas. Thank you for your attention. I welcome questions.
Thanks for that. For the first part of your talk, I was interested, did you take into account or have you experimented with provenance of the actual extraction methods, or have you only looked at the provenance of the web sources of where it came from?
Yeah, so this is a good question. We essentially treated the extraction system almost as a black box. So we said, you know, our mantra was this is a very complex process with many gears, thousands of extraction patterns. It's very hard to reverse engineer the workings of it. So we just used these provenance breadcrumbs and type information like, you know, object type and things like that. There's definitely better things, I wouldn't say better, more powerful things possibly that you can do if you open this black box and look a little bit and try to reason about exactly how all the gears work. So there's more things that we can definitely do there for sure.
Thanks.
Hi, thank you very much. This is really interesting. One question I had about the second part, the source selection, is there could be sources that are pretty good on the head facts, those for which you are most likely to have statistics, but really poor for tail facts. Is there a way of that you tried or consider modeling what might be the case, the tail? Because the tail is where extraction really is useful. Because the head would know all of it, right?
Yeah, so in our objective function, we're trying to balance the gains of new triples versus the cost of extracting them. So whenever a slice, a web source plus slice descriptor covers a lot of existing triples and few new triples, then that slice is unlikely to get selected because what we count as gain is the new triples that we would gain into the knowledge base rather than the existing ones. So if a source is already full of head facts, and those head facts are already in the knowledge base, those are going to get discounted from the cost function to begin with. Now there is the issue, what I glossed over a little bit here, is that I am using as a proxy of the information that the source contains, the facts that have been automatically extracted from the source. So if I see a few new facts from, let's say, tail entities, something that is not already in the knowledge base, that I say, okay, this counts as 5 new facts. But it's possible that the source has a lot more. I just haven't seen evidence of it. So when I'm comparing, I'm trying to decide slice 1 or slice 2. I'm just going by the evidence that I've seen rather than the true data that may be there, and I just may not have seen evidence of it.
So I maybe not explain myself well.
Okay,
what
sorry.
I'm worried about is that those tail facts, those new facts, may be actually wrong, but you don't have a way of estimating that because this source was very good on the head facts.
I see. So the way we go about, so we don't try to estimate the quality of the facts. We take the labels that the automated extraction process gives us as a fact. If it has high confidence, we consider it good quality. We don't try to validate it ourselves.
Thank you.
All right, let's thank Alexandra again. Next up, we have the